All right, we've got our next to last topic. There's one more topic that will be tomorrow, but we've got our next to last topic for the quarter. This is thin-walled pressure vessels. So we're going to think of spherical and cylindrical thin-walled pressure vessels. There would be a difference between thin-walled and thick-walled pressure vessels, and we'll talk about that when we get to it. But let's get over here to OneNote and start kind of talking about how we're going to deal with these thin-walled pressure vessels. So the first one we'll deal with will be a spherical one. So this could be like a basketball. There's some butane tanks that are spheres, something like that. So let's try to create one over here. Let's make it an actual sphere or circle, and let's go ahead and erase half of it so that we can cut it open. I'm going to cut it open right through the center of it, so right through one of its diameters, and that'll be the worst case scenario for this pressure that we want to figure out here. Let's get this guy there. Get another one of those, make it smaller. That looks good. All right, so there's our cut open spherical but thin wall pressure vessel. By thin wall, our criteria is that we need some dimensions. Let's label some stuff and then we'll do the criteria first or after that. So first thing we need to know is going to be R. R is going to be the internal radius of the thin wall pressure vessel. And T, we'll use a lowercase t, is going to be the wall thickness. And our criteria that's going to separate thin wall from thick wall pressure vessels is going to be that the radius divided by the thickness T needs to be greater than 10. So basically the radius, internal radius, needs to be large compared to the wall thickness of this thing. 10 is, I suppose, maybe not a hard and fast number, but it's a cutoff point between thin wall and thick wall pressure vessels. So the equations that we'll derive today are only going to apply to thin wall, the ones that actually meet this criteria. So our thin wall pressure vessel here has a stress in the wall. I'm going to draw a couple of arrows kind of showing that there's this stress in the wall of the pressure vessel. This is the stress that we are going to calculate. If the stress gets too large, then this half of the pressure vessel has separated from the half that we erased. So we're going to call this stress sigma A. And we're going to say that it's evenly distributed around this ring here. It looks like maybe I drew a few more arrows on this front side than the back side, but that's not on purpose. I just, for whatever reason, drew more on that side. So it is evenly distributed around there, and it's distributed on this wall. I'll try and, get some shading here to kind of show the cross section of the wall. I don't want to go into too big a detail here and take forever drawing these little hash marks. Good enough. So that blue crosshatch area is the wall that's experiencing this sigma A axial stress, or the stress in the wall of the pressure vessel. The pressure that's causing this stress, I'm going to draw it. Let's see what color. We haven't used green. It's going to be green today. So this pressure is some kind of, there's some kind of liquid, or, well, not liquid necessarily, some kind of fluid. So it could be air, it could be a liquid or whatever, but it's pressurized inside here. And I'm going to, I did use green for the radius. What other colors do I have? I have this yellow. We'll do this yellow. So this surface here, I slice through the fluid that's inside here. The pressure is acting. I'm going to just draw one arrow for this pressure and label it P. And that P is going to be the internal pressure. So we'll put that over here. P equals internal pressure. So you look at your basketball and it tells you to inflate it to 18 psi. That 18 psi would be the internal pressure. All right. So we know stress equals force over area divided by area. You know, we actually did this like the first or second day of the course, talking about stress is force divided by area. So what I want to do here is say that, well, the stress is, I've labeled that as sigma A. That's the stress in the wall. If that stress exceeds the material strength, so the yield strength even, then I've stretched this thing out beyond its permanent or its shape, and I've permanently deformed it. And so that's bad. Or if I add even more stress, then it's fractured and now it's exploded, so that's even worse. So that strength needs to compare to the stress that I'm about to calculate. The force here would be the force in the wall. I haven't really described that yet, but I drew these arrows that kind of show the stress in the wall, so that stress is created by a force. And then the area would be the area of the wall. So the area of the wall is this blue hash that I have drawn here, and let's give us a little more room. Now I could do this, right? So there, put another one there and make it a little smaller. So that area is this area here. I'm gonna kind of quickly make it blue crosshatch. So I could take two different circles, subtract the inner one from the outer one, and get this blue area, and that would be the area of the wall that this force is acting on, or I could calculate the stress in the wall. I'm going to take a little bit of a shortcut though, and this is also one of the things that makes this not work for thick-walled pressure vessels. Also the fact that I'm assuming, I'm a little bit off the screen, aren't I? Let me slide over here a little. There we go. I'm also assuming that this stress and therefore the force is evenly distributed around the circle here, the circular cross-section ring, but it's a thicker wall pressure vessel. That would not be true. It wouldn't be evenly distributed from the inner surface towards the outer surface. So both of those combined together make this really only applicable to thin wall pressure vessels. So I said both. So one of them is the uneven distribution in a thick wall pressure vessel. The other one is what I'm about to do to calculate this area. So what I'm going to do is a little bit tricky, and it seems a little unnecessary, but it's going to give us an approximation that's close enough, and it's an easier calculation. Not that it's particularly hard to calculate this area, but what we're going to do is I've got this ring here, and I'm going to slice it open right there, and I'm going to lay this side down flat and lay this side down flat, which will give me something like this. Except it would be there. Oh, hold on. Let's make it outlined in black like the other piece. Something like that. Let's do a little blue shading. So you kind of see I've sliced it up and laid it out flat. So this dimension is that wall thickness, and this the length of it is basically the circumference of the original circle. And I'm going to use pi times 2 times r, where r, if we go back up here, r was the inner radius up here. So that's another reason that it won't quite work for thicker walled pressure vessels, because that difference between the inner radius and the outer radius is probably significant on a thick wall. But for this one, a thin wall, then they're pretty close to the same thing. So for this length here, I'm going to use the circumference being 2. You could just do 2 times diameter, but a lot of the times these equations are going to include a radius in them. So although radius is typically not the thing that you talk about if you talk about a pressure vessel. Like if you have a basketball, you don't say, oh, that basketball has a radius of 9 inches. You say it has a diameter of 18 inches. But in this equation, we're going to use that internal radius instead of a diameter. So 2 pi times r will be this length here. So that makes the area of the wall equal to 2 pi r times the wall thickness. So that's our area that can go in that equation at the top of the screen in the denominator. Now we need to work on the force in the wall. So let's plug in area of the wall into our equation and rearrange the sigma A equation to say that force, I'm going to do F wall equals sigma A times the area of the wall. So all I'm doing is rearranging that equation up there, and I am just solving it for force. And we did just find out the area of the wall to be 2 pi r t. So I've got this for the force in the wall. Okay, so just a minute ago we wrote this equation: stress equals force over area. That same thing is how you calculate pressure. So pressure equals the force divided by the area that force acts over. Oops, area. So it's just like a stress, except it's usually not thought of as a stress. Stress is like an internal, and remember we defined it to be the intensity of internal forces. Pressure is more like a force that's applied to an outer area somewhere. It's like a pressing on it or something, pressure. So they calculate the same way, they have the same units, but we typically think of them as different functions. So let's write this equation: pressure equals the force from this pressure divided by the area that the pressure acts on. So let's go back up here. I said that this yellow area inside of our pressure vessel is where the pressure acts. So that's just a circle, pi r squared. Again, I'm using radius instead of diameter here. So pi r squared. I'm going to solve this equation also for F. So I've got F related to the pressure equals P, the internal pressure, times pi times r squared. All right. Now what I'm going to do is, let's go back to this picture. I have drawn it, I could have oriented this sphere in any position, but I've drawn it so that the forces are acting horizontally. So the pressure force is, I drew one of them, but it's really spread out over that entire yellow area. But it's acting to the left, and it's off the screen here, but the pressure associated with the sigma A, the stress on the wall of the pressure vessel, is acting to the right. And there's a whole bunch of those, but they're all pointing to the right. So what I'm going to do is I'm going to do a force balance in the x direction. So these pressures are associated with forces. I just solved for the force in the wall and the force from the pressure. And I have equations for both of those, and they need to balance. So I'm going to take these two forces, and I'm going to write summation of forces. I drew these in the x direction. Again, I could have drawn them in any orientation, but x equals 0. I drew the force in the wall going to the right, so it'll be a positive force. sigma A times 2 times pi times r times t. I drew the pressure going to the left, and so its force is also going to the left, minus p times pi times r squared. So all I did is I put the equations in for these two things that I just calculated, the two forces. I put their equations. So the one sigma A 2 pi RT is F wall minus F pressure. Need to add to 0. Well, so I guess plus, I should probably put plus in there, but I don't want to deal with what it's actually going the other direction. So I'm saying that they need to subtract together. But I suppose technically they need to add together, and one of them is negative. So what I've got now, though, is I can say that, well, these need to balance. So I can put p pi r squared on the right hand side of the equation, and I've got this other thing on the left hand side, and what I want to solve for is sigma A. That's the stress in the wall. That's the thing that matters, right? So the stress in the wall gets too large, it exceeds the yield strength of the material that the pressure vessel is made of, and I have yielded the pressure vessel, which made some part of it thinner, which is probably going to lead to some cascading effect of it failing and exploding, or at least popping or whatever. It's going to have a hole in it. So that's going to be bad. So I can take this equation, solve for sigma A, and I end up with sigma A equals p pi r squared over 2 pi r t. So the pi ends up canceling out. The r squared cancels out with the r, and this equation just simplifies to sigma A, the stress in the wall of a spherical pressure vessel, equals p r over 2t. And that's all there is to the equation. That's the stress in the wall of this is a thin wall, so thin wall, and it is spherical pressure vessel. So couple of caveats there. It is the thin wall pressure vessel. It is a sphere, so it's not one that's a different shape. There are other stresses, like we could have chopped up this circle, just a little sliver off of one end. We could have sliced it up over here or some other position, but this stress is the worst case for the stress in the wall of the pressure vessel, as long as it's a spherical thin wall pressure vessel. So that equation is pretty straightforward. I think I've got a problem over here that we can look at. I'm just going to copy it and paste it in. So came out a little bit small. We might have to that's really small. Let's see if we can zoom in on that somehow. There we go. Oh, it's got a misspelling in it too. That should be, I wonder if I can fix that. There we go. A spherical gas storage tank. So that's what we're dealing with. So this one should be a thin wall pressure vessel. It has a diameter of 32 feet. So an inner radius, or a radius, that's probably the outer diameter. Inner radius of 16 feet. And a wall thickness of almost an inch, a little over 3/4 of an inch, 0.875. What's that, 7/8? So that's probably qualifies as thin wall. Let's check just to make sure. I don't think the problem here is going to, be a trick problem or anything. But let's zoom out so you can see the whole problem there. All right. So let's just see. The radius is equal to 16 feet times 12 inches, so 192, and that's probably the outer radius. So technically the inner radius is probably subtract off a wall thickness, So 192 minus 0.875 is 191.125 inches. Probably that's the technically correct thing. And the wall thickness was 0.875 inches. So the ratio of R to T is equal to 191.125 divided by 0.875, 218. So yes, we're way over the 10 limit. So we're definitely in the thin wall pressure vessel realm. So that's good. Determine the maximum normal stress, which is this equation that we just developed here. That is a normal stress. You know, if we go back to our picture, those arrows are all perpendicular to the blue surface that they're acting on. So that's the definition of a normal stress. So determine the normal stress in the tank if the gas pressure, meaning the pressure inside the tank, is 125 psi. So let's take our equation. And I might have to zoom out. This is like gigantic on my screen. So let's go back to something a little more reasonable. So sigma A equals P R over 2T. P, 125 psi. So that's pounds per inch squared. R technically is that internal radius. 191.125 inches. It probably would make no difference if we used 192 in here, but that's technically the inner radius over 2 times the wall thickness of 0.875 inches. So we have pounds per inch in the numerator per inch, so that's going to give us another pounds per square inch, which is going to be a stress unit, so that will work. Let's see, 125 times 191.125 divided by 2 divided by 0.875 is 13,651.8 psi. So this would be compared to the yield strength of whatever this material for this pressure vessel. It's got to be, you know, I guess it doesn't have to be, but it's some kind of metal for a gas tank usually, but it could be some other material. And that's probably a safe pressure or safe stress, safe pressure that generates this stress for this material. So that's good. All right, let's talk about the cylindrical pressure vessels. So we could take this again. I'm still zoomed in really far, so let's zoom out a little bit. We could take this exact thing, right? Copy it and drop it in over here, and so this is exactly the same as what we had, but let's just change this end over here and make it something like this. Whoa, 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 whoa. I wanted to, oh, well, there we go. I can't get it to do what I want it to do. There we got it. All right, and now we need to make another one of these arcs. See if we can do that. Something like that. And then we'll copy we'll erase this. I guess we could have made that a dotted line, but that's okay. We erased it. So the exact same thing as the sphere, but now we have a cylinder that we chopped in half. So a cylinder at least has this. So cylindrical pressure vessel. Would have the same stress in it, and we would call this the sigma A again, you know, the normal stress, P R, same variables, 2, T, all that's the same stuff. We could call it the longitudinal stress sometimes. That might be another word that you see for this. If you think about a longitudinal axis, you know, through the pressure vessel, you can see how that would work. But there are other ways that we could slice this pressure vessel that would create different stresses. So in cylindrical pressure vessels, you do have this stress, this longitudinal stress or this normal stress, but you also have what's called a hoop stress. So the hoop stress ends up being a worst case scenario for cylindrical pressure vessels. So that's the one that we usually need to work through, although they do have this normal or axial or longitudinal stress. So how you would get to the hoop stress is you take your cylinder and you slice it. Actually, you slice it on a plane here, kind of like this axis, this longitudinal axis that I drew. So you slice through the long direction of it. So you would end up with something. Well, let's see if we can draw this. Let's see. That's going to work maybe. And up here, we need it to be kind of in 3D. And maybe something like this. For whatever reason, it doesn't like me to grab those pieces. This will work here in a minute, I think. Well, I want to get both of those. Not like that though. Put them over here. All right, now we got to do some erasing. So let's erase the top half of our cylinder. And let's erase the top half of this part. We'll fix that part in a minute. Okay, and we've got a little edge there, edge there, edge there. That's kind of okay. Let's put these back together. And then we would also have a bottom to it down here. Huh, wonder why that's not. Oh, it's because it's going to line up over there. I'll just draw that because that's going to not do what I need it to do. So it's going to come off something like that, I guess. Well, we'll cheat. It doesn't have to be perfect for our picture. We'll just do that. And then, well, let's erase this so we can kind of see in there. And then we need to put our wall in here. So something like, we'll just freehand it. Now, the end conditions, the end caps on these cylinders, you could have spheres on the end. You could have stuff that's indented inwards on the end. You could have flat ones on the end, and they all have different effects. The end caps do have effects on the cylindrical pressure vessels. We're ignoring those effects for now. Actually, for this course, we're ignoring those. So if you go on to do some more work in an advanced class beyond this one, then you would probably consider those end caps and what effect they have. But now, let's create the same variables that we had before. So we still have the radius, R. We still have the wall thickness here. Is that on our screen? Yeah, barely. We might need to move over a little bit. There. Let's see, the radius, we still have the length L. We'll put that one right here. I think we just, well, I don't think we were ever naming it L when we did that before. Actually, I guess we didn't have L. This is the length of the pressure vessel, ignoring the end caps. These are the little surfaces that we're thinking the pressure is in. So this one and this one. A lot of little blue lines. And then we've got this surface that the pressure is on. So that's going to be this surface here. I'm not going to solidly color it in, but that surface. So the pressure here, this is called the hoop stress. So it kind of goes around the hoop of the thing. And so the stress, the hoop stress, sigma h, is what we're going to use for that, is this little set of arrows. And they would also exist on this side. Maybe I shouldn't have drawn this so big. It's taking a, there we go. And then there's the internal pressure. I'm going to draw it as a single large arrow kind of here. That's P. So those are all the same things that we had before. And we're going to do the exact same approach to develop this equation. So we're going to say that sigma h, that's the hoop stress, equals the force in the wall. So the force associated with all those tiny arrows, divided by the area that they act on. So there's two areas. There's the little blue hatches in the back and the blue hatches in the front. So there's two of them. And one of them would be L times T. So that's their area. So we could have this rearranged to say, well, the force in the wall is equal to the hoop stress times 2 times L times T. Okay. Then we're going to go in and say for the pressure, P equals the force associated with the pressure. And it acts on the area, the yellow area here. So that's 2R. So that's the diameter times L. And we can rearrange that equation to solve for the force associated with the pressure equals the internal pressure times 2 times R times L. I drew all of these arrows. Again, I could have oriented this any particular way. I drew it so that the arrows, even though the P arrow is kind of crooked there, it's pointing straight down, and all the wall arrows are pointing straight up. So I can do a force balance in what I would call the Y direction and say that, well, the wall force is sigma h times 2 times L times T, pointing up, and the pressure force is P times 2 times R times L, pointing down, and those have to add to 0 to be in equilibrium. And then I can solve for sigma h. So the hoop stress equals P times 2 times R times L, just move that to the other side of the equal sign, divided by 2 times L times T. So the 2's and the L's cancel out, and I'm left with the hoop stress equals P R over T, which is twice the axial stress. The axial stress, or the longitudinal stress, or the normal stress, whichever one you want to call it, it was PR over 2T. This one's PR over 1T, so the denominator in here has a 1, so it's going to end up being twice the stress as the longitudinal one. So that's why we're normally concerned with the hoop stress for these pressure vessels, the cylindrical pressure vessels. Now again, the end caps on these cylindrical ones do have an effect on pressures that you would deal with. You can combine the longitudinal and the hoop stress together to get some stress at an angle. You might want to do that if you've got a weld seam that goes around here at an angle and you want to find the stress on that weld or something like that. None of those things are things we're going to do in this course. What we're going to do in this course is this equation, sigma h equals PR over T, and the the one that applies to the sphere and the normal stress in the cylinder, PR over 2T. So really straightforward equations, nothing tricky with these problems. They are really straightforward, and you'll have some of these on exam 3, maybe one or two at most of these on exam 3. Well, I'm just looking to see if we've got a problem. We do have one here that we can work on. Let's just copy it and solve it. All right, so here's our problem statement. Pretty small. Hopefully you can read it. I'll read it so that you can actually tell what it says. I don't want to zoom out again though. But it says a cylindrical propane tank. So the cylinder that we just dealt with has an outside diameter of 4 meters. For some reason it copies ands as AMD for some reason. I don't know. And a wall thickness of 20 millimeters. So again, that if we took the radius of 2 meters and a wall thickness of 20 millimeters, that's definitely going to fall in the thin wall pressure vessel range. If the allowable hoop stress is 120 megapascals and the allowable axial stress is only 55, so I actually have a stronger hoop stress than I do axial stress, determine the maximum internal pressure that can be applied to the tank in megapascals. So I actually have to solve both of these to figure out which is the worst case scenario. Or I can just think about it and say, well, there's a ratio of 2 to 1, right, in between the hoop stress and the axial stress. Let's grab our axial stress equation. Oh, didn't want it to draw. There we go. Get that guy. And put that down here. So I've got these two equations. Both of these stresses exist in this cylinder. And if I'm looking at the allowable stresses, the hoop stress is more than twice the allowable axial stress, right? So even though it's going to be a larger hoop stress, twice that of the axial stress, the allowable stress to exist in the axial direction is less than that. So you could just, if you don't want to work through which one of these do you need to solve for, you can just work both of them and figure out, well, which one allows for the smallest internal pressure. That's your limiting case. So it's going to be our axial stress that limits it. So we would just have sigma A equals PR over 2T for the longitudinal stress, or as they said here, the axial stress. And they're only going to allow 55, I'm going to go times 10 to the 6 pascals. So that's 55 megapascals. They're only going to allow that. P is what we want to know, is how much pressure can we have in here and not exceed this allowance. R, again, we know the outer diameter is 2 meters, or well, outer radius is 2 meters. But technically you're supposed to subtract off the wall thickness. Again, these numbers are going to be to the point that subtracting off that wall thickness really doesn't matter. But just to be completely accurate here, we're going to do that. So we're going to subtract off 0.02 meters. And then we're going to divide by 2 times our wall thickness, 0.02 meters. And I'm just converting the millimeters over to meters so that I have all the same units, so that when I solve this, I'll end up with pascals for my pressure. So let's see if we can put the numbers in here. So we've got 55 million. Oops. Let's move the denominator over, so times 2 times 0.02. And then let's divide by 2 minus 0.02. And I get a bunch of ones. So I get P equals, I think, 1.1 times 10 to the 6 pascals. I think is what I get there. I'm just checking. Well, I'll try to check. we could do the same equation if we weren't sure if the axial stress was the real limiter. We could check the hoop stress, sigma h equals p r over t, and we have a different allowance for hoop stress. We have 120 times 10 to the 6 pascals equals, clicking the wrong screen. There we go. 100 p, which we're trying to solve for. R is the same, 2 meters minus that 0.02 meters over a thickness of, well, and just not 2, just 1 t, 0.02. So from this set of equations, we get P equal to 120 million times 0.02 divided by 2 minus 0.02, and I get 1, 2 repeating, 1.2 times 10 to the 6 pascals. So comparing these two, I'm limited by this one. It only lets me have 1.1 megapascals, whereas the hoop stress would let me have 1.2 megapascals. So that would be the other way to solve this, is just solve for both cases and see which one is the real limiter. So that would be the complex version of one of these problems. They're actually quite simple. The equations are really straightforward. You do have to remember them, though. They're not going to be given on the exam anywhere, so you do have to remember these two equations and when the hoop stress is the one to use. So you use the hoop stress for cylinders. You only use the PR over 2T is the only equation you have for the spheres. But you also have both of these equations for cylinders, and you have to make sure which one you want to use. In this case, you needed to use the axial equation. It was the limiter. All right. That's all there is for pressure vessels, thin-walled pressure vessels. Again, there are more to it if you start considering the end conditions, spherical end caps or concave end caps or flat end caps. That's not what we're going to consider in this course, but that is a consideration to have if those end cap conditions matter for what you're doing. And this is only good for thin-walled pressure vessels. So the pressure vessels that meet our, where'd I put it? I think it's right up here. Radius to thickness ratio of greater than 10 or more. All right. Well, we will be back tomorrow with one last topic, a manual way to do stress concentrations. We've done a little bit of that, not necessarily with that intent, but we have looked at that in SolidWorks simulation, but this is doing it by hand. Not doing finite element by hand, but how you can use some empirical charts that, well, actually, I think they're not empirical. They're actually theoretical charts, but they are going to help us find maximum stress from something like a notch or a transition somewhere from a large area to a small area or a hole in a plate, something like that. So that'll be tomorrow. Now we'll see you all on tomorrow.